You already kind of see what's going on. So we're going to finish part 2. Actually, I have a handout for you. And then we're going to skip 3 and 4, we're going to go to 5. Because actually 5 talks about something called the Uranus plot. Hey, Mike. And we need to get to that before Thursday. And then Wednesday we'll finish 5 and go back to 3 and 4. Make your head spin. Okay, and Thursday, I think it says number 9 and 10, but we're only going to do number 9. So yay. But you will need to do a semi-formal lab report for that one. And then we're bumping up against spring break. So next week is the week before spring break. That's right, yeah. So you guys are gonna take your Unit 2 exam a week from Thursday. Probably, I think, in the same room for the whole semester. All right. So, do you have something handed, Mike? Okay. So the homework that y'all did actually was to come up reaction orders with regard about using inspection. Yes.
We have till 4 to turn that in.
Yeah.
Or does it do it at the time?
No, yeah, well, 3-ish. But if you have it done by 4 and slip it under my door, that's fine with me. So that would be good. That would be preferred than not doing it. That'd be great. So the whole by inspection. Wait, first off. Well, you guys will probably. Do I need to do this? I will. Here in a minute, we're going to switch gears and we're going to do 2 reactants. One reactant is going to be called Q, which I'm not sure why. Goes to form products. Okay, we can write the rate law expression for this as reaction rate. We can go initial or just plain old reaction rate is the rate law constant K times the molar concentration of Q raised to its reaction order, I'll call that M, times the molar concentration of R raised to its reaction order, I'll call that N. Okay? And units of reaction rate needs to be moles per liter per time, and a good time is seconds. Okay, it doesn't have to be. So you guys actually came up with these by inspection. And I think in order to kind of make that clear, what I'm going to do by inspection, that is, how do I say this? You're doubling the molar concentration of your reactants and looking for a difference, what effect it has on your rate. Now, what I need to do here in the rest of this part is I'm going to talk about an algebraic approach. And an algebraic approach, you're going to run these experiments. These are like 4 different experiments, or actually I should just say 2. You only have to run 2. You can run a couple of experiments with different molar concentrations of R, okay, reactant, and you're going to get different rates. And we compare, it's not doubling though, and this actually was Mike's question the other day. If you don't double it systematically, and you see a change in reaction rate, how can we use that to get to our reaction orders? And I'm going to show you it has to do with logs. So the algebraic approach, this last approach, this is what you guys did in lab, okay, graphically. Okay, what you did in lab where you actually, you ran using different concentrations of a reactant, okay, and you take the log of the rate, okay, and actually should give you a positive slope. This is a very ugly thing, but the slope then, M is equal to your reaction order. Okay, that's graphically, right? So that's what you guys did in lab. So let's take a look at the algebraic approach. So like I said, in algebraic approach, you basically, and we're going to see the data where you run at least a pair of trials and you change the molar concentration of reactant and you look for the changes in the rate. But you're not necessarily doubling the molar concentration. So this is what I put on the board, where we have 2 reactants, Q and R, go to form products. And you can see we didn't double. But a good thing about this little pair of experiments is, what did we do with R? We kept it constant. So that, actually we had to do that. But we definitely, this is not 2 times, okay? But I'm going to show you how we can get to the reaction order M, okay? Using these molar concentrations and their relative reaction rates. Okay, so I mentioned that we're going to be using logs. So I printed this out. I usually at this point in the semester, I don't know if I give it to you, Chem 1, this is Chem 2. Now this won't be, you don't have this sheet for your test. But in case you're kind of unfamiliar, and I told you I'm not a math teacher, with how logs work, for instance, we said, well, if we go over here to exponents, we said anything raised to the 0th power is 1. So there you go. That's just a law. That's the way exponents work. But over here, for instance, we're going to use this here in a minute. Do you see the first one where it says log? Lowercase b means any base. It could be log base 10 or it could be the natural log. These work. The log of the product of x and y, we can break it out into the individual logs. It's equal to log of x plus log of y. That's going to help here in a minute. The other one, the third one down, is also going to help. It's awesome. If you are wanting actually the exponent of something, okay, the log of something raised to a power is equal to that power times the log of that thing. And that's actually what this says. So it's log base b of x raised to the n is equal to n times log base b of x. That is so helpful. So those two, actually. So here we go. So we could write the reaction rate like this, okay? This is the rate law expression for this reaction. Okay, again, R in our two trials is constant. So here in a minute, we're gonna use that to our favor. So, we know mathematically if you have an equality like this, you can divide both sides by the same thing and it's fine. So here we go. We're actually going to take, for the second trial, oops, I hope you guys can read this, it's kind of purpled out. If we say rate 2 for the second trial is equal to the molar concentration of Q at the second trial, raised to its reaction order, times the molar concentration of R, which was constant for both trials, raised to its reaction order, times K, okay? And we do a similar thing for the first experiment, rate 1, okay? Now, if we divide basically rate 2 by rate 1, we can do on the other side what you see done here. The cool thing about this is, I just think this is so cool. I was looking at this earlier. Okay, so these are that's our last column, our rate 2 and rate 1. This is our first column, I guess it was. But do you see where these are the same? Does that make sense? Why are they the same? Well, they were the same in the experiments I did. Are these K's the same? Yeah, the K's are dependent upon temperature only. Yep, they're the same too. So life is we have just done something that's kind of helpful. We can basically say the ratio of the rate of the second experiment divided by the rate of the first experiment is equal to, now I've done kind of a thing that's legit. Okay, basically I said over here, okay, I have the molar concentration raised to m of Q2 divided by the molar concentration raised to m of Q1. I can take the ratio of Q2 to Q1 right here and take that power outside. So far, so good? Okay, so now actually, is this where I'm going to do it? I'm going to take the log of both sides. I can totally do that. I'm going to take the log of the ratio on the left is equal to the log of the ratio on the right. Now what I'm going to do is actually, is this when I'm going to do it? I think so. I'm going to apply that third rule here that I have, where that thing over there on the right, I can say that over there on the right, that is actually equal to m times the log of that ratio. Oh, awesome. Totally awesome. Okay? So we're almost done. I mean, then actually on the next slide, I think all you're going to see is and keep your wits about you, if I want to solve for m all I have to do is divide both sides by this. Okay, so basically move that over there. That's it. So we have now a way to algebraically knock out what your reaction order is for the reactant Q. That's assuming like it was, R canceled out and all that. We good with that? I am. So if you go back a few slides, you can see what we can substitute there. Okay? So for rate 2, it was 0.0104 moles per liter per second. For rate 1, it was 0.00668 moles per liter per second. Notice units cancel there. Down there in the denominator, we have the molar concentration of Q2 is 0.212 moles per liter. The molar concentration of Q1 is 0.170 moles per liter. Now, I'm not sure if I was doing this, I think this sort of problem, and I don't, you notice I didn't use units here of moles per liter per second, and I didn't use units here of moles per liter, but they both cancel out, so. All right? So now this is the sort of problem, if you're like me, I usually have to do it a few times to make sure I get the right answer. What you might want to do is actually take the log, and I might do this here in a minute, I think. You take the log of this number, you write it down, you take the log of this number, you write it down, and you do one last division. That's the safest way. That's what I think. Or actually, I see I did the ratio, and now I'm going to take the log. Now, for a lot of problems for you guys in kinetics, coming up with those reaction orders, a lot of times they're going to be these nice whole numbers like 1 and 2. 0, hopefully you recognize that there's no change, right? Yeah. So if you don't get 1 or 2 or 1.5 or something that has these, then you might have done something wrong. Okay? So I didn't take a look at these, but let's take a look at these together right quick. So you guys did 14, 11 today, and then 12 and 13 will be due. Now for 12 and 13 will be due on Wednesday. For 12 and 13, you're going to see that it's not systematic. It's not like doubling. You have to do this algebraic approach, I think. Let's see what my hints are. There you are. All right. Okay, so we have 3 trials here, 2 reactants. And so what I do usually is write down my generic rate law expression. Okay, it just gives me warm and fuzzies. So we are after these M and N. Okay, notice that we're also after K, but if you get M and N, remember it's kind of like the homework that was due today. If you get M and N, you just pick any experiment, substitute them in, knock out your K. All right. Let's see, I say focus on experiment 1 and 2 to get M. And this is kind of that you probably recognize the green equation. Okay, just like in class. Now I say use experiments 2 and 3. If you do it in this order, at this point you have the reaction order of A. It's not going to be as neat and tidy, and they won't cancel because A did change from 2 to 3, but you're okay. You can actually knock that out, okay? So that term does not go away, okay? All right. That's my hints for that one. All right. The next one, let's see, 2 reactants. It's easier than 12. Oh, okay. My hint in blue says since 1 and 2 double, you can go back to by inspection. Okay, that's what I would do anyway. See how the rate changes and see if it's 0 first or second. Use ratio to determine it, and then what do I do? And then I would go to 1 and 3. where NO doubles, oh, I don't know. Maybe this is like back to just plain old by inspection. Okay? Maybe it's not an algebraic approach. That's what I'm reading in my notes. So I'll push these out there. Okay. All right. Love those rate laws expressions. So this, remember, like your lab that's due Thursday, all you got to do is write up your calculations. This is just like your lab. And I'm going to show you why it works. Okay, so what you did with your lab was you did different concentrations of one reactant, holding the other one constant. Okay, and got the rates. And then you switched. You held the one that varied last time, you held it constant, and you varied the other. Okay, so you did 8 trials, and actually we're going to do an example like that. But why does it work that way? Okay, so the rate law expression for A plus B, you guys got this? Okay, good. The rate law expression looks like this, where it's always the molar concentration of the reactants raised to reaction order times the rate law constant. There's your rate law expression. Yep. So back to your law of logs. If you look at the first one, it says you can take the log of both sides, okay, and we're going with the natural log, and it could be log base 10 for this one. The only one you can't do log base 10 was the Clausius-Clapeyron plot for whatever reason. I asked my husband, I'm like, well, why can't you do log base 10? He's like, it doesn't work that way. Okay, but these you could do either. So anyway, if we take the natural log of both sides, what we're going to do is take the product on the right, which is K, molar concentration of A raised to its reaction order, molar concentration of B raised to its reaction order. We're going to separate that out. And as I separate that out, I want you to keep one thing in mind. Let's consider a scenario where, let's see, in which only the molar concentration of A is changed. B is held constant. Okay? Now, in that case, B is held constant. Check this out. If B is held constant, by golly, I'm just going to put it with my other constant, kind of like I did that pseudo-constant before. Okay? So I'm breaking out the product of K times molar concentration of A raised to its reaction order times molar concentration of B raised to its reaction order. I'm breaking it out to 2 terms, just according to that first law of logs you have there. Okay? And the reason I'm breaking out this way is because B is constant. All right. Well, see that first term right here? We have something really awesome happening here. Because if you take the natural log of something raised to a power, it's equal to that power times the natural log of that thing. And what are we after? We're after m. So that's wonderful. So that actually ends up looking like this. So all I did here was to move that m over in front of that natural log. Perfect. Nothing else has been changed. Well, now finally we have something that actually we can plot. So kind of superimposed underneath, I put y is equal to mx plus b. So if on the y-axis, just like we did, we plot the natural log of the rate, or it could be log base 10 of the rate, and along the x-axis, if we go ahead and plot actually the natural log of the molar concentration of the thing that's changing, which is what you guys were going to do, make those plots, okay? Then it's funny, m and m. Okay, there are 2 different m's. M here is the reaction order, and what's this m here? The slope. Yeah, m is equal to m. Okay, the reaction order of A, which is m, is equal to the slope of your line. Now, we don't do much with it as far as I know. What's B? What's B and y is equal to mx plus b? Remember? Some intercept. It is the y-intercept. Very good. Okay, the y-intercept actually is equal to this. So, that's a thought. Okay, so we just did it. That's it. Okay. So this actually kind of, this is the law of logs. This is that first law that I have. And then the second one up here is the third law, the law of logs that I have on your sheet. Okay. Very good. So bottom line, and this is kind of what you guys are gonna be handing in Thursday/Friday, you're gonna have two plots, and you plot the log of the rate, oops, and you plot the log of the molar concentration, positive slope, that's it, okay? All right. So, like you guys did in lab, then you switch it up. If you have two reactants, you did 4 experiments where you varied one and 4 experiments where you varied the other one. Okay? So, this is where we're varying B but holding A the same. And notice we can kind of do the same thought process, come up with something that we can plot. Where now, if we plot along the x-axis, the log of the molar concentration of B, along the y-axis, the log of the rate, our straight line will give us the reaction order of B, which is N. It doesn't have to be N. You guys should be a rebel and make it some other variable. It really doesn't matter, I don't think. Okay. So then one more, or you guys, that's 2 of your plots. Your third plot is very exciting, I think. Your third plot then is to get to K. By this point in your calculations, you have the reaction orders of A and B. You have M and N. Okay. To get to K, all we have to do is simply plot the rate along the y-axis and this whole blob along the x-axis. Now, what is that whole blob? Well, it's the product of each of the reactants raised to the reaction orders, which you already know. So this is where actually that last one, you guys are going to have actually 8 points. Plain old rate here, and this is the molar concentration of your 2 reactants raised to their now known reaction orders. Straight line, here's your 8 points. And I think they usually kind of come in pairs. It's just kind of how it works, I think. And your slope M is equal to your rate log constant K. Okay. Any questions about that? So
What's the B on that one? Or is it
I was thinking about that. I think it should go through the origin, I think. Let's see if it does. Does that mean? I think it should be 0. We'll see. Okay, so here is your example where we have 2 reactants, NO2 and O2. So we're going to do 8 experiments. Basically, one is to vary the NO2, and the other 4 experiments is to vary the O2. All right. Seems kind of anticlimactic, I think. So that blue line demarcates, if you kind of get your bearings about you. In the first one, looks like we are varying these guys, holding these guys constant. In the next one, we are varying these guys, holding these guys constant. Okay, and these are the rates. So looking at the first 4, first, to get the reaction order of NO, looks like this. Or that's the raw data. Okay, that's the molar concentration of NO, your other one was constant, and these are the reaction rates. So we're getting ready to do this to it. Okay, so we need to have, you're going to use Logger Pro to come up with 2 calculated columns, and they're going to look like this. Okay, so this calculated column was the natural log of the rate. This calculated column was the natural log of the molar concentration. This is going to go on your y-axis, and this is going to go on your x-axis. And it should look like this, something like this. So you see the 4 data points, going to be kind of like yours because you'll have 4 data points too. And then down here, we're looking at correlation coefficient, looking pretty good. Positive slope, looking pretty good. Slope of 1.99. I can live with that. Look like 2 to you? Me too. So the reaction order with regard to that reactant is 2. Awesome. It looks so easy when I just flip through the slides like this. All right, let's look at the second set of 4. So where the O2 varied but the NO was constant. Again, we need to go ahead and use LoggerPro to come up with 2 calculated columns. This is the natural log of O2 and this is the natural log of rate. We're going to put rate along the y-axis and put O2, natural log of O2, along the x-axis. And it should look like this. So correlation coefficient of 1, that's pretty darn good. Looks like our slope is 1.02. What do you think? 1. Yeah, reaction order with regard to that reactant is 1. So now we can go back to our generic rate law expression and go ahead and substitute a 2 for M and a 1 for N. So our rate law expression, to me, if somebody asks for you to come up with the rate law expression, they don't necessarily want a value of K there. They just want you to throw in the K, but they want you to come with your reaction orders. Okay? So that's NO raised to the second power times O2 raised to the first power, molar concentrations of. And we're almost done. Okay? So like I said before, now what we're going to do is going to plot rate along the y-axis, and we're going to plot this actually along the x-axis. And then our slope is going to be K. Oh, one thing before I go, and we're going to kind of take a look at why this is significant with regard to this particular problem. Remember the overall reaction order, okay, is in this case M plus N, which is what, 2 plus 1, which is 3. Okay, that actually has consequences. Your overall reaction order actually will set the units of K. You know, K is, the units of K is a weird thing, I think. Remember I said the units of K kind of have to cancel out what is introduced by your molar concentrations and leave you with units of moles per liter per time for your rate. All right, so to get to that last one, you're going to need these 3 columns. These are all 4 plus 4, you know, both sets of trials. And you're going to have 1 calculated column. So that 1 calculated column basically takes NO2 raised to the second power times NO raised to the first power. That's what your calculated column does. Because remember, LoggerPro is great at just kind of pulling a column in, square it, times pull the other column in. And it will load that up for you to put along the x-axis. So then all we're going to do is that's going to be your x, and this guy's going to be your y, and we're going to call it good. I don't necessarily see them paired up. Some of them are maybe. So these are the 8 points then of rate versus molar concentration of NO squared times molar concentration of O2 raised to the first power. It's NO squared, not NO2 squared. Any questions? So that's your, and actually I don't have a problem like this, but you're doing it for lab anyway, so it's not a problem. But one last thing I want to revisit. Oh, before I go. Okay, so from here, correlation looks great. Correlation coefficient looks great. Slope is 7.1 times 10 to the third. Now, slope is equal to K. That's easy enough said, but I'm going to have to kind of revisit Y units are actually going to be, units here are liters squared per mole squared per second. I'm not real thrilled how that kind of, I hate those slashes. Liter squared per mole squared, also in the denominator second. Sometimes I would actually kind of say that's 1 over moles per liter squared times seconds. That's probably, I don't know if that's what I would do, but they mean the same thing. You buy that? Liter squared per mole squared. Okay. So why is that? Well, this was our rate law expression. We came up with second order for NO and first order for O2. We know that the rate, the units of the rate needs to always be moles per liter per time. In this case, moles per liter per second. That's our target. And if we think of it this way, where kind of this blank here is the units for our K, and we recognize that with the NO, we're squaring it, and with the O, we're taking to the first power, okay? So in order to make it all right, the units actually of K have to be this, okay? Because mole squared in the denominator of K will cancel, let's say, that mole squared. Liter squared in the liter squared in the numerator of K will cancel with these liters squared, and you're left with units of moles per liter, and then also in the denominator second time, okay, which is, you know. So it was that third, and we didn't do one of these before. We didn't come up with a, like the units, if it's overall second order, needs to be inverse time, okay. If it's first order, it was, no, I'd have to look back at it again. But we did, I think we might have done 0 first and second, and this is third. So that's what the units need to be. If I have to do it, I usually kind of think through it again, because I don't memorize it. I just say, well, what K has to be in order to cancel what I introduced with my reaction orders. Okay. So let's go see how far we get talking about in part 5. We were skipping ahead to part 5. And it looks like this. I started to, panic's not the right word, but I started looking at when your test is and what we need to get through. I'm like, I'd like to just go home or go have lunch or something, but we really do need to get down the road. And specifically for your experiment, we need to make sure we get this under our belt. But parts 3 and 4 are really awesome. Okay. It's like somebody looked at the factors in why a reaction rate proceeds how it does, and they said, dude, we ought to be able to kind of pick that apart. That is so cool. So if we just kind of simply say there's 3 things that affect how fast a reaction occurs, we go back to these 3 things, okay, are they going to collide, or how frequent will they collide? And actually this first term, I don't know if you remember, but I said that's concentration all the way. So in your reaction rate, that's your molar concentrations raised to the reaction order. We have these 2 other factors then, the energy factor associated with the rate of a reaction and the orientation factor that still need to be addressed kind of behind the scenes in our reaction rate. So I think I'll put it up here. Oh, I should just left that up there. Let's go A plus B goes to form some products. The reaction rate is equal to the rate law constant times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. And there's these 3 things that affect it There is collision frequency. And collision frequency comes from those two terms. The molar concentrations actually raise the reaction order. And then the other two are energy factor and orientation factor. And guess what? The only other place these two things can come from is right here. And that's where they come from. And that's what we need to talk about. Okay. So the K, that rate law constant, it's for a specific, well, it's for a specific reaction rate of a specific reaction, and it's a specific temperature. Okay, so that K must include both the energy factor and the orientation factor. Don't blame me, because actually I have another K coming up. Like, are you serious? And we're still not done. We have more K's coming up. So this equation will be on your sheet, but you just need to know how to use it. So the Arrhenius equation, and actually here, and I don't think we'll get to it today, but we can actually take this and do something cool with it. Involves logs, and actually plot it to understand more. But this K in the Arrhenius equation is this K. Are you guys good with that? I think I am. And this K is equal to K0, another K, times E raised to the EA. I'll have to explain what that is, but that's the activation energy. EA divided by RT, but that's to the negative power up there. And maybe not so surprising, since this seems a little complicated, the T needs to be in units of Kelvin, so don't make that mistake. T needs to be in the absolute temperature scale. So the way this works is, I just think this is so cool. This K0 actually covers the orientation part, and the EA covers the energy part. You're like, that is just so cool. So here we have totally dissected the rate law expression, I think. Okay, now, you see that link up there? On my Twitter feed today, I actually posted this Arrhenius. I posted a link for a few reasons. Let's see if it comes up. The Arrhenius equation. Okay, first off, and I think your textbook might do this, and sometimes I forget to tell students this. A lot of times in the Arrhenius equation, instead of a K0, you actually see the A star. Okay? So it's the same thing. It's a constant. It's an orientation. It's handling the orientation part. Okay, so if your textbook says the Arrhenius constant, it's the same thing as my K0. Okay. Another thing is this actually, see these blue links right here? Do you kind of see where the rate law constant K, we've been talking about, actually is broken down into this A or K0, and then raised, this is like, I don't know what E is, it's got an actual value. And on our calculators, you see the little E raised to the X, okay? Your activation energy, I'll just put it this way. Activation energy, a variable. Temperature, a variable. Activation K. I guess they're saying K is constant. Our K is given. Anyway, I'll put 3 stars here. I haven't tried it yet, but it kind of says, like, if you plug in, if you know 2, it'll spit you out the third one, which is kind of nice. So that's all. Okay. Back to the notes. So the Arrhenius equation. K0 will actually carry the units of K. Remember, K0 and A star or A0 are the same thing. That second term, that E raised to the negative EA over RT, that's unitless. But in order for that to be unitless, actually, this power up here, this guy needs to be unitless, okay? And it will be unitless if you go ahead and I said make sure that your units of temperature are in Kelvin. Make sure your activation energies are in kilojoules per mole. And then also use the value of R as 0.00833145. In other words, 8.3145 times 10 to the negative third kilojoules per mole. So if we kind of focus on this up here, I'm going to go ahead and plug in those units just for kicks. We said EA needs to be kilojoules per mole. And then we said R, with that value, will have units of kilojoules per mole Kelvin. I love making units cancel. And then we said temperature is going to be units of Kelvin. So by my estimation, my K's cancel and my kilojoules per mole cancel. So it all works. Now, if you ever get stuck working a problem on a grad entrance exam or a scholarship exam, you know, go back to the units and go like, oh, okay, that all works. Okay, so this again could be A star or A0, okay? So this K0, my orientation factor, okay, it actually represents the number of situations in which the reactants are successfully oriented so that they can proceed from reactants to go to form products. Our energy factor is the second term in the Arrhenius equation. Our energy factor would be this E raised to the negative EA over RT. It's kind of funny because we're going to be kind of monkeying with the temperature, but can you see where if the temperature is in the denominator of an exponent, you're like, well, if you increase that, it seems like it would decrease your term, but then it's raised to the negative power, which then kind of reverses that. So if you increase it, actually it increases, and it does. If you increase temperature in this setting, you're going to increase that term. So that's kind of neat, I think. All right. So let's take a look at activation energy. What in the heck does that mean? Well, we're going to bring in some energy diagrams. And we're going to put activation energy in terms of what does activation energy, sometimes called activation energy barrier, an energy barrier. What does that look like if your overall reaction is endothermic or exothermic? Let's see if you guys remember this. So our enthalpies. What is an enthalpy for an endothermic reaction? Is it positive or negative? You guys remember? Yes, very good. It is positive. Perfect. Yep, endothermic's positive. Exothermic then negative. Yep. Good job. Well, we're going to see, and actually I don't mean to throw you out by saying endothermic and exothermic, doesn't matter. They're always going to have an energy barrier in order to proceed from reactants to products. Sometimes I think life's full of little energy barriers. Okay, like, so we're going to look at an exothermic process first. If it's exothermic, then that means actually energy is released. So energy is released as on an energy diagram by showing you that I have less energy than I started with. Energy is released from my system. So this would be a negative enthalpy change. So the activation energy barrier, to get to that, you see the hump there, hopefully, right? You basically take the initial up to the top of the hump. That is your activation energy barrier. This down from initial to the final, that is your enthalpy change. Oops. No, my battery's not running out. This is my negative delta H, but this right here is my barrier. And sometimes it'll be a big barrier, sometimes it'll be a little barrier. But all reactions, as they proceed from reactants to products, have it. They're like opinions. Everybody has one. So there's your EA. So if that's exothermic, endothermic reactions have an activation energy barrier. So endothermic would look like this. Energy is required for it to proceed from left to right. So we can show that by showing the final state at a higher energy. Energy is required. Is this right? Yeah. So we can knock out the delta H, which will be positive. There's my delta H. And here is my activation energy barrier. So it goes again from the initial up to the hump. Initial up to the hump. Oops. And okay. So that's a good place, I think, to stop. So you have two problems related to algebraically coming up with reaction orders. They're fun. So on Wednesday, we'll finish this part and then go back for 3 and 4.